Hello everyone. Today we're going to talk about TextFlows, which is a visual programming platform for text mining and natural language processing. What is text mining? Text mining is a research area that deals with the construction of models and patterns from text resources, aiming at solving tasks such as text categorization and clustering, taxonomy construction, and sentiment analysis. Sometimes it is considered as a subfield of data mining. And from a procedural point of view, 6 steps are proposed for text data mining. These are base understanding, data understanding, data preparation, modeling, evaluation, and deployment. The TextFlow platform described in this paper is a new open-source web-based text mining platform that supports the design and composition of scientific procedures implemented as a executable workflow. As a fork of CloudFlows, TextFlow has inherited its service-oriented architecture that allows the user to utilize arbitrary web services as a workflow component. TextFlow is oriented toward text analytics and offers a number of algorithms for text mining and natural language processing. The platform is implemented as a cloud-based web application and attempt to overcome various deficiencies of similar text analytics platform. Workflow components, which is in this paper they call widgets, and the text flows are organized into packages, which allows for easier distributed development. The text flows packages implemented several text mining algorithms from Latino, NLTK, and scikit-learn libraries. Moreover, TextFlow is easily extensible by adding new packages and workflow components. Workflow components of several types allow graphical user interaction during runtime and visualization of results by implementing views in JavaScript, HTML, or any other format that can be rendered in a web browser. On this paper, firstly, we're going to talk about the technical background and implementation details. Then the concept of the workflows going to be described, and implementation, execution, and sharing. Also, widget repository and the implemented module of the platform. We're going to talk about them, and lastly, we're going to see some use cases that has been executed in the TextFlows. The TextFlow platform, as you can see in this figure, there are two. The TextFlow platform has two parts. The one is front end, and the other is back end. The back end is the blue section that you can see on the right side. The backend comprises this relational database for storing workers for task execution, and a broker of delegating tasks from different queues to workers, which can reside on different clusters of machines. The front end is designed for user interaction with workflow through the graphical user interface in a web browser. The backend of the TextFlow platform uses Django, which is a Python-based open-source high-level web framework. Django follows the model view controller architectural design, which encourages rapid development and includes an object relational mapper and template engine for efficient code generation. TextFlow task queues are used as a mechanism to distribute works across threads and machines. This is performed via Celery. The Celery communicates via messages and use a message broker to mediate between clients and workers. TextFlow uses the PySimple SOAP library for integration of web services as workflow components. PySimple SOAP is a lightweight Python library which provides an interface for client and server web services communication. The client side of the TextFlow platform consists of operations that involve user interaction primarily through the graphical user interface in a modern web browser. The graphical user interface is implemented in HTML and JavaScript with an extensive use of jQuery library. The key concept used in the text mining and natural language processing are documented collection or corpus, single document or text, or a document feature or annotation. Each TextFlow document collection is represented by an instance of the annotated document corpus or ADC class. A single text is an instance of annotated document class, while the feature are instances of the annotation class. The size of the document collection may vary from a few to million of documents. More is better, for sure. In TextFlows, the Python class that represents a corpus of document is called annotated document corpus, or short the ADC. The features are stored in a simple key value Python dictionary where keys are strings and the value can store any Python object. In TextFlow, a single textual data unit within a collection by collection means like a document, is represented by the class annotated document. Similarly to annotated document corpus, annotated document instances is in TextFlows also contains features which may provide information about a single document. In TextFlow, annotation instances are used to mark parts of documents. Every annotation instance has a two-pointer, which one points to the start and the other to the end of the annotation span in the text, in the document text. Well, what is the concept of workflows? A workflow is an executable graphical representation of a complex procedure. The graphical user interface used for constructing workflow follows a visual programming paradigm. The most basic unit components in the TextFlow workflow is a processing component, which is represented as widgets in the graphical representation. So here in this picture, in the left side, you can see the widgets. Different processing components are linked by a connection through which data is transferred from a widget's output to another widget's input. The TextFlows GUI consists of a widgets repository and a workflow canvas. So here in the right section, you can see in this section, you can see the workflow canvas. The widget repository is a set of widgets ordered in a hierarchy of categories. The workflow canvas implements moving, connection, and issuing commands to execute or delete widgets. Every action on the workflows canvas causes an asynchronous HTTP post request to be sent to the server. The workflow execution engine is responsible for executing the workflow widgets in the predefined order. Two such engines are integrated into the TextFlows platform, one implemented in Python and the other one is implemented in JavaScript. Well, the subparts of the workflows in subprocesses and loops are executed by the Python implementation, while the top-level workflow executed from the user interface are processed by the JavaScript implementation. With the Python implementation, the server receives only one HTTP request for the entire part of the workflow, and when a workflow is running with the JavaScript engine, it perpetually checks for widgets that are executable and execute them. Executable widgets are widgets which either have no predecessors or the predecessors have already been successfully executed. Each widget is executable through a synchronous HTTP request. When a widget is prepared to be executed, a task is added to a suitable task queue, as some widgets have special library requirements or even system requirements, as they're executed on a separated task queue with its dedicated worker. Celery communicates via messages and uses message broker to find a suitable worker to which the task is delivered to. Dedicated workers process monitor task queue for new work to perform, and when the task is executed, its result is saved into database and returned to the client, and the execution of the workflow is considered complete when there are no executable or running widgets. Workflow and TextFlows are processed and stored on a remote server from where they can be accessed from anywhere, requiring only an internet connection. So by default, each workflow can only be accessed by its author. The TextFlow platform generates a specific URL for each workflow that has been saved as public. Users can simply share their workflow by publishing the URL, and whenever a public workflow is accessed by another user, a copy of the workflow is created on the fly and added to the private workflow repository. Then the workflow is copied with all the data to ensure that the experiments can be repeated. Widgets in TextFlows are separated into 4 groups based on their type. One is regular widget. Well, the regular widgets perform a specific task that transform the data from their inputs and parameters to data on their output, and provide success or error messages to the system. Visualization widgets are extended version of regular widgets, and they also provide the ability to render an HTML template with JavaScript to client's browser, which is useful for data visualization and presentation of a more detailed feedback to the user. Interactive widgets are extension of regular widgets, as they pop up an additional window during execution through which the user can interact with or manipulate the data. Workflow control widgets provide additional workflow controls which allow the user to combine different workflow components into subprocess and provide different types of iteration through data. Widgets also categorized based on their functionality. So one is text mining widgets, which is a collection of implemented text mining widgets. These widgets are further divided based on their text mining functionality. Basic widgets are the widgets that are responsible for creating and manipulating simple objects such as strings and integers. A collection of workflow control widgets are called subprocess widgets, which are required for visual programming of complex procedures. And workflow components representing the WCL web services that are the user has imported. Documented acquisition, or so-called import, is usually the first step of every task where TextFlows employs various widgets to enable loading document corpora, labeling of documents, with domain labels and converting them into the annotated document corpus structure. We identified the following text document acquisition scenario, which are also supported by the development widgets. The TextFlow document corpora can be uploaded from local files using the load document corpora interactive widgets. The user can integrate third-party web services as a workflow component using the import web service button obtained from the bottom of the widget repository. And the TextFlow platform support the loading data only from MySQL database via the load document corpus from MySQL widgets. The crawl URL links widgets receive as an input a list of URL like a Wikipedia page, and in the TextFlow the user can search the web search with Bing or, for example, Faro widgets, which they use Microsoft Bing and Faro as their web search engines. TextFlow implements widgets which allow the manipulation of annotated document corpus data objects or ADCA data object that allow the user to add new features, extract existing features from the document corpus, split document corpora, merge different corpora, and etc. A special widget in the platform is Document Corpus Viewer, which visualizes the ADC data objects. As you're going to see in the next slide picture, this one, the Document Corpus Viewer interactive widgets allows the user to check the result of individual widgets by visualizing the ADC data objects from their outputs. Through its interactive interface, the widget allows the user to select an individual document from the list of documents snipped by simply clicking on it. This opens a new page with a detailed view of the selected documents. Well, here you can see how these widgets working through like the stopboards and tokens. I'm going to talk about it in the next slides. Processing is a very important part of any form of knowledge extraction from text documents. Its main task is to transform the main task is a transformation of unstructured data from text document into a predefined well-structured data representation. In general, the task of pre-processing is to construct a set of relevant features from a text document. The set of all features selected for a given document collection is called a representational model. Each document is represented by a vector of numerical values, one for each features of the selected representational model. Technically, our implementation employs the Latino, which is link analysis and text mining toolbox software library, and NLTK library, which is a natural language toolkit library, and scikit-learn library for the text processing needs. A standard collection of pre-processing technique is going to talk about it. They're together with the sets of functionality implemented in our platform, in the TextFlow platform. Tokenization. In tokenization, meaningful tokens are identified in the character stream of the document, such as words or terms terms. The TextFlow offers a large set of tokenizers from Latino, for example, such as Max Entropy Tokenizer, Unicode, Simple, Regex Tokenizer, and etc. Stop words are predefined words from a language that do not carry relevant semantic information. The usual practice is to ignore them when building a feature set. In TextFlows, we have 3 widgets which are used for stop word tagging. These 3 are get a stop word set, stop word tagger, and a stop word tagger hop. Tagging annotation words with the appropriate part of a speech tags based on the context is which they appear. Brill's rule based post tagger or classify based post tagger or post n-gram tagger. This is a process of converting word tokens into their stem or citation form. The most common document representation model in text mining is the bag of words model, or for short BO model. One of the most important characteristics of the described document feature is that the fact that they are usually very sparse, meaning that most of the feature in a vector have 0 weight. This sparsity is due to the fact that there are many different features in the document corpus, yet a single document contains only a small subset of them. The TextFlow platform uses the compressed sparse row matrices or CSR matrices in order to be able to efficiently store the matrix of features in memory, and also to speed up algebraic operation on vectors and matrices. In data mining modeling phase, each document from the ADC structure needs to be represented as a set of document feature it contains. In TextFlow, the construct BO dataset and BO model constructor widget is these 2 widgets takes as an input and ADC data object as and generators as a sparse BO model dataset. The widget takes as an input also several user-defined parameters which are taken into account when building the feature dataset. Token annotation. This is the type annotation instances marking part of the document which will be used for generating the vocabulary and dataset on a dataset. The feature name, well, if present, the model will be constructed out of the annotation feature value instead of the document text. Subword feature name is an annotation feature name which is used to tag tokens as subwords. These tokens will be excluded from the BO representational model if the subword feature name is not provided. All tokens are included in the BO space. Label document feature name is the name of the document feature which will be used as a class label of the example in the dataset. If this part is blank, that means the generator's sparse dataset will be unlabeled. The maximum word frequency, cutoff frequency value for including an item into the vocabulary. The word weighting type. Well, the user can select among various weighting models for assigning weight for features. And normalized vectors or the weighting methods can be further modified by the vector normalization. The documented classification, or called text categorization, refer to automated assigning of predefined categories to natural language text. The primary application of text categorization system is to assign subject categories to document to support information retrieval or to aid human indexer is in assigning such categories. The term supervised learning refers to the described approach to automatically building a text classifier from training document, which have been labeled or often manually with predefined classes. The TextFlows platform currently contains only the supervised learning approach from the Latino, NLTK, and scikit-learn libraries. The example for these three libraries, you can see it like the nearest centralized classifier or naive bias classifier is an example for Latino libraries, or the multi-nominal naive bias classifier is an example for scikit-learn libraries. There are many. But basically, for training and applying classifiers, TextFlows offers two dedicated widgets. One is to train classifier hub, and the other is apply classifier hub. The train classifier hub receives on its input a sparse feature dataset object and an untrained classifier. The apply classifier hub receives a trained classifier object and return predicted class probabilities for every new document from the input test dataset as well as the test dataset with a new predicted label columns. The literature-based discovery refer to the use of paper and other academic publication to find new relationship between existing knowledge. So the TextFlows platform includes a dedicated categories with several widgets with support literature-based discovery. For example, literature-based discovery is supported through the incorporated Explore in Crosby widget, which provides a link to the web application Crosby. The noise detection filtering is frequently used in data pre-processing to improve the accuracy of include classifier. The classifier, the TextFlows incorporates an ensemble-based noise ranking methodology for explicit noise and alt-layer identification named NoiseRank, which the NoiseRank was modified to work with text and TextFlows ADC data objects, and its main aim is to detect noisy instances for improved data understanding, data cleaning, and alt-layer identification. The TextFlows platform enables the user to create interactive charts for easy and intuitive evaluation performance results, and it includes a standard performance visualization used in machine learning, data mining, information retrieval, or etc. Notably, the TextFlows platform includes a fully methodology named Viper, which is a visualization approach that displays the result as a point into two-dimensional precision recall space. This platform contains several visual performance evaluation widgets, which results in interactive performance charts that can be saved and exported to several formats. These charts are like scatter chart, which is what these charts include: ROCS space chart and PR space chart. Case chart, curved charts include PR curves, cost curves, lift curves, ROC curves, Kendall curves, and rate-driven curves. And column chart, these charts are generally column charts for visualizing multiple performance measures for a set of algorithms. So we're going to look at some of the use cases that show how exactly the TextFlows platform works. So in this use case, you can see the sub-process in the TextFlows platform for a comparison of part of a speech post tagger on the same categorization problem. This use case basically shows these workflow is for evaluating 7 classifiers from different text mining libraries. As you can see in the left side here, these are the classifier. The top 4, these top 4, which is nearest centroid classifier, naive Bayes classifier, maximum entropy classifier, and KNN fast classifier, they are from Latino library, and the other 3 in the bottom 3 are from scikit-learn library. Here shows the for loop sub process which evaluate the input classifier using tenfold stratified cross validation and extract the obtained result, which are then visualized in the first use case that we saw in this use case. This one, you can see the for loop here. Here is the use case for that for loop. Here, this use case is a sub-process workflow representing the methodology in every fold for the use tenfold cross validation. First, the construction of the training and testing sparse matrices is performed. Next, the input classifier model is fitted to the training dataset and used to predict class probabilities for every new document from the input test dataset. The sub-process returns constructed pairs of actual and predicted classes. The first sparse bow model dataset and the bow model constructor instance were generated by the constructed bow dataset and bow model constructor. So here in the middle you can see the bow model constructor. We constructed unigrams, which basically n-gram, but here only the n is 1, so it's a unigram, out of the stem value from the word tokens, while the disregarding stopwords in the process. And the bag of words vector here on the left, the bag of word vector space was calculated using the TF-IDF weighting scheme. The test sparse matrix is required to be constructed using the same parameter settings, IDFs, and vocabulary as the training sparse matrix. Therefore, we apply the bow constructor object to test the ADC data object using the create bow dataset using the bow model constructor. And after that, we after calculating the training and testing sparse matrices, we fitted the input classifier model to the training dataset using the train classifier here in the top, the train classifier hub. Then the apply classifier hub received the train classifier object and returned the predicted class probabilities to every new document from the input dataset. So here in this diagram, you can basically it's visualization of classifier evaluation in the precision recall plane where each point here on the top right corner represents the result of an algorithm. So those points which are closer to the upper right corner have higher precision and recall values. As you can see, the scikit-learn's SVM linear classifier and the Latino's maximum entropy here, the maximum entropy classifier achieved the best result. The workflow used for evaluation of five different post taggers from various text mining libraries on a text categorization problem. So post tagging, here you can see the 5 post tagging post taggers. The post tagging widgets from NLTK requires tagging sentences data as input, which is used for training the post taggers. Here, the sub-process workflow representing the methodology in every fold for the use 10-fold cross-validation. First, the input post tagger. Is applied to document corpus. Then the construction of the training and the testing. The construction of the training and testing sparse matrices is performed. Then a linear SVM classifier is fitted to the training dataset and used to predict class probabilities for every new document for the input test dataset. And finally, the subprocess returned the constructed pairs of actual and predicted classes. And then the last use case, the noise rank workflow using the implemented classifier used for class noise detection. You can see in this use case, the noise rank methodology workflow returned a visual representation of a list of potential outlier instances and ranked according to their decreasing number of noise detection algorithm, which identified an instance as noisy due to its classification into class different from its own class label. Well, thank you all. I hope it was useful, and again, thank you very much.